Greetings to you. Welcome to the next class on potentiometry. We were discussing about the electrical double layer. So, what I had told you that when transfer of electrons from the electrolyte to the electrode or vice versa can occur only between the electrode surface and the liquid junctions around it. A thin layer of solution I asked you to imagine, and then I told you that around the electrode there will be all cations will be moving towards the cathode and all anions will be moving towards the anode. So, when a positive voltage is applied to the electrodes to the system, there will be a momentary surge of current occurs which rapidly decays to 0 if there is no chemical reaction, that is no transfer of electron. So, this current is known as charging current that creates an excess of positive ions near the cathode if there is no reaction and negative ions around the anode if there is no reaction. So, there will be around the cathode in that small space containing the cations of the same shape as the cathode surrounding it, there will be deficiency of anions, and in the anode section in the same space there will be deficiency of the cations. So, there will be excess charge of the cations and negative charge excess charge of the anions around this thing. And then I had also told you that immediately surrounding it there is a compact inner layer of the solution. The potential will decrease linearly with distance from the electrode surface, and there is another portion where the potential will decrease exponentially. So, this entire array of charged species and oriented dipoles at the electrode solution is known as interfacial diagram. Yesterday I had taught you all this, and I had shown you this figure. So, this is the electrode surface, positive ions are here, this is the immediate space around it, and then slightly different space around it, that is of the order of about 20 angstrom units. Here it will be about 300 angstrom units, and this will be the bulk of the solution. So, in this region there is almost a linear decrease in the electrode potential, and in this region D1 to D2 there will be exponential decrease of the charge potential. So, according to Faraday's law, this also we had covered yesterday. So, electron transfer occurs easily from the electrode to the chemical species in the solution, because the amount of chemical reaction occurring is proportional to the electrode current. So, that is Faraday's law. So, under certain conditions, even when a cell voltage is applied to a cell, the electron will not have sufficient energy to get reduced or oxidized. So, what happens? This could there will not be any reduction reaction or oxidation reaction. So, since the conditions of redox reactions are not met, the ions will be hanging around without transferring the electron to the electrode or without any chemical reaction taking place. So, applied electrical energy is consumed but converted to heat by friction associated with the motion of the ions. Therefore, the ions in the electrical double layer rearrange and adjust to new potential, and this new potential behaves as a capacitor. Such a process is called non-faradaic process, and the current is called as non-faradaic current. Okay. So, when Faradic current flows in a cell, continuous mass transfer of reactive species takes place from the bulk of the solution to the electrode surface through convection, migration, and then diffusion mechanisms. So, convection results from the mechanical motion of the solution molecules, solvent molecules, as a result of stirring or flow through the solution, etc. And migration occurs due to the movement of the ions due to electrostatic attraction, that is positive attracting getting attracted to negative, negative getting attracted to positive, etc. And diffusion occurs due to the motion of the species carried by a concentration gradient. That means, the apart from these two mechanical processes, there is another species, another phenomenon that is taking place through which ions will move, that is known as diffusion. So, a major series of analytical methods are based on the electrochemical properties of the solutions. So, a solution of the electrolyte contained in a glass vessel in contact with two electrodes which are connected to an outside source of electrical power can cause a current to flow through a cell. This is galvanic cell, what I had already described to you. So, what are the different types of electrodes we use? I have been talking about electrodes, etc., and I have also told you that electrodes can be made of any metal that can pass the current, and there has to be some sort of reaction at the electrode surface, either it is cathode or anode. But there are other kinds of electrodes. For example, look at the first one, that is inert electrode. What is an inert electrode? An inert electrode is a metal piece that is used to make electrical contact with the solution, but no chemical reaction should take place with any component. Such an electrode is known as inert electrode. Usually it is a noble metal electrode or graphite electrode. You know graphite, lot of pencils use graphite, writing pencils, they use graphite cylinder like thing in the pencil, that also can be used as a inert electrode. So, platinum, gold or silver or a simple carbon electrode gives good results as an inert electrode. So, then we know another term that is known as active electrode. So, an electrode made of an element in its uncombined state which will enter into a chemical equilibrium with the ions of the same element in solution. That means, whatever I am studying, the whichever metal ion, the electrode has to be made of the same element. If I am studying silver, then my electrode should be silver. If I am doing it with mercury, it should be mercury electrode. If it is hydrogen, it has to be hydrogen electrode, like that. So, that is known as active electrode, that will enter into a chemical reaction in our experimental setup. Then we have gas electrode. What is a gas electrode? A gas electrode is nothing but a small platinum wire or a foil with gas bubbling over the electrode. Okay. So, what I do is, normally I take a beaker, put a platinum electrode, bubble the gas through that is all. There is nothing very special about gas electrode. Okay. And then we define what is known as cell reaction. So, whenever a direct current passes through an electrolytic cell, oxidation or reduction should take place at the anode and cathode respectively. This you already know. At the anode, oxidation takes place with transfer of electrons from the reduced species to the electrode. At the cathode, reduction takes place and the electrons are transferred from the electrode to the oxidized species. So, external circuit carries the electrons from anode to cathode, the electrical circuit is completed by ionic conduction through the solution. This is the typical setup of a cell reaction. So, I can write the generalized redox reaction like this: R molecules of A that is a reductant can react with S molecules of B as a oxidant, and that will react with P to give you P molecules of A as the oxidant, that is species A is getting oxidized from reduced species, and B is getting reduced to B is oxidized species is getting reduced to reduced species. So, I have written here R S P Q. So, if both sides are equal, R is equal to same number of molecules, R is equal to P, that is same number of molecules getting oxidized. For the oxidized molecules are same as reduced molecules, and same thing here with respect to the other party, that is B and reduced oxidized species and reduced species. I can write K is equal to A oxidant equilibrium constant, that I am writing the product divided by the reactants, A oxidant, B reductant at equilibrium concentration, and A reductant and B oxidant at the equilibrium So, this has to be a constant because both the forward and reverse reactions are occurring. After some time there will be equilibrium. This we have already discussed number of times. But I can also write a thermodynamic expression, that is Q is equal to A oxidant, same equation basically, but instead of writing EQ equilibrium, I am writing activities. Okay, A oxidant of activity and activity of the species B as reduced species divided by activity of A species as a reductant, that is a reactant here, and B activity of the B as oxidant. So, from thermodynamic consideration we have two quantities now, K and Q, and these two are related by thermodynamic equation considerations with respect to related to free energy, that is delta G is equal to RT ln Q minus RT ln K, that where R is room temperature, this gas constant 8.316 joules per mole per degree, and then T is temperature, ln Q, that is activity minus equilibrium RT ln K. So, this is a very important relationship between activity and equilibrium reactions. So, this is a very standard form of expression in all equilibrium reactions. So, we also have another relation, that is delta G is equal to minus N into F into E cell. Okay. So, this expression also comes from thermodynamics. We are not going into details of that, but since we are going to use this equation, I am starting from here. Delta G is equal to minus NFE cell. You can look up the thermodynamics books to find out how this expression is valid, how it is derived. Okay. So, in this expression I have E cell is equal to potential in the volts, and F is Faraday constant, that is 96,500 coulombs, and N is the number of electrons transferred per 1 mole of unit reaction. So, I can write E cell is equal to delta G, I can write E cell is equal to delta G, I transfer all these parameters this side. E cell is equal to delta G by NF, there should be one minus sign here. that is equal to minus RT by NF ln Q and RT by NF ln K. This expression is obtained by equating the previous equation, that is RT ln Q minus RT ln K. I am replacing delta G with that expression, delta E cell is equal to. So, look at it. Now I can write E cell, I can reorganize this Q. I am going to put the value of Q and value of K in terms of activity coefficients. Okay. So, I can write E cell is equal to my RT by NF ln A oxidant divided by A reductant minus RT by NF ln A oxidant activity, A reductant activity, P is the stoichiometry that comes in the exponential form, P, Q, etc. So, this quantity minus RT by NF with respect to B, that is reactant B oxidant at equilibrium raised to Q divided by B reductant at equilibrium raised to Q minus RT by NF ln same thing as this, except EQ replaced by activity. This expression I am going to write E naught. There is some difference. Okay, RT, this is known as E naught at equilibrium minus RT by NF ln B reductant divided by B oxidant raised to Q activity divided then B oxidant reductant raised to Q of the activity. Now, we are not using concentration terms. Similarly, minus of E naught A and RT by NF ln A reductant raised to P of activity, again A oxidant raised to P activity. So, this whole thing E naught minus RT by NF ln B reductant divided by B oxidant raised to Q and activity term I put it as EB, that is a potential corresponding to B, because here everything is B, this whole term, and then this whole term refers to redox reaction of the species A in terms of thermodynamics and equilibrium concentration. What I have done actually is I have taken the terms corresponding to A and corresponding to B separately and reorganize the equation here. Okay. So, put them together and then equilibrium concentration I am going to put it as EA, EB and EA corresponding to each species. And so, the cell potential what I am going to get out of this reaction, which reaction? The top one. Okay, A reductant, B reductant, oxidant, reductant. So, the cell potential of the reduction reaction, redox reaction of A, B will be given by the actual potential difference between EB and EA, where EA is nothing but E naught A, this part E naught A minus RT by NF ln A reductant raised to P activity, NF ln A oxidant P activity, and EB also similarly. So, these equations EA is equal to E naught A, these equations are known as Nernst equations. So, Nernst equations are the they tell us about the actual potential of a given system for each element. Okay. If it is A element, EA I can write EA is equal to E naught A minus RT by NF ln A reductant divided by A oxidant raised to P and all in terms of activity. Similarly, EB. So, this is the Nernst equation for A and this is the Nernst equation for B. Okay. I can write the previous equation, that is Nernst equation EA is equal to E naught A etc. in terms of a reduced species and oxidized species. R molecules of A reductant goes to P molecules of A oxidant and plus Ne minus, it has to be it has to be associated with the release of electrons, and then or I can simply write A oxidant plus Ne goes to A reductant. If N is equal to 1, A oxidant Ne number of electrons that goes to A reductant. Similarly, I can write N number of electrons can combine with S molecules of oxidant and Q molecules to give you Q molecules of B reductant. So, here S and Q should be same equal number. So, here I can simply write B oxidant plus Ne goes to B reductant. Okay. So, for convenience all half reactions are written as reductions. This is a convention we should learn. So, whenever whatever is the positive value we write it, but you write it simply as negative. Even if the value is negative, you still write as the negative as a reduction. Convenience, it is only our convenience, we can write either way. So, the overall reaction is obtained by subtracting one of these, that is the quantities E naught A and E naught B. This should come here, E naught A and E naught B, this B should be here, are called as standard potentials for the half reactions and can be evaluated by setting a reaction in which for one half cell the ratios of activities are unity and the logarithmic term becomes 0. So, no valid method has been discovered for setting up only a half cell. I cannot carry out a half cell reaction in any of the only half cell without that is either oxidation or reduction. To take place, for oxidation to take place, there has to be another species to take the electrons, otherwise I cannot just deduct the electrons etc. So, I cannot write either oxidation or reduction as a single entity. So, no valid method has been discovered for setting up only half cell, since a measurement always requires a second electrode. To complete the circuit, I need a second electrode. Therefore, it is necessary to choose an electrode to arbitrarily assign a 0 position on the scale of potentials. So, standard hydrogen electrode, SHE means standard hydrogen electrode, has been selected for this purpose. So, this is an electrode in which hydrogen is bubbled at partial pressure of 1 atmosphere over a platinized foil in an aqueous solution in which the activity of hydrogen is unity. So, if I want to compare different kinds of redox reactions undergoing by any species, I must write reactions like this: A oxidant plus Ne goes to reductant, B oxidant or plus Ne goes to B reductant. For convenience, I write all half reactions as electrodes, and the value of the reduction potential will be different for different elements. Okay. And because the values are different for different elements, I need to know which one is having higher value, which one is having lower value. That means, now I am going to create a scale in which I can compare, this is a better reductant, this is a better oxidant, the one which is having higher value is a better reductant. The one which is having lower value is a not so better reductant, or it could be an oxidant also. So, either way. So, to compare every redox reaction, I need a comparison standard, but I cannot have a comparison standard with only half cell. I have to measure with another half cell, and that half cell, other half cell is nothing but a hydrogen electrode. That hydrogen electrode, by convention, we are giving it a value of 0, that is standard hydrogen electrode. So, the standard hydrogen electrode has been selected for that purpose. So, the potential of standard hydrogen electrode is 0.000 according to our convention, used only for our convenience. But if I can set up a redox reaction using hydrogen with another metal. Okay. So, I can compare all the metals with respect to hydrogen, because by convention hydrogen is 0. So, this is the whole idea of having a comparison of redox potential, which is a better reduction reagent, which is a better oxidation reagent. Okay. So, we continue our discussion on the different types of electrodes. We will continue our class in the next session. Thank you very much. Have a nice day.